Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is my quarantine hair. And I would like to welcome you to the summer 2020 offering of ECE3084 Signals and Systems. Let's talk about how Laplace transforms and Z transforms are well suited for their particular domains. So we've been using Laplace transforms primarily in the context of studying differential equations, and we discovered that if we take the derivative of a function that corresponds to multiplication by s in the Laplace domain, and you could stop here if you assume that the initial conditions are 0, otherwise you would need to subtract those. Similarly, in ECE2026, we primarily studied difference equations in which the main operation was to take a delay. And what we discovered is that if you delayed a signal by one time unit, that corresponded to multiplying the Z transform by z to the minus 1. Now, if you wanted, you could plug e to the s in here, maybe just normalize and say that Ts is equal to 1, and write down some sort of Laplace-y kind of thing. And you could work with that, but it would be kind of annoying because this weird variant of the Z transforms would have all this aliasing business going on. And also, instead of having this nice multiplication by Z here, you would have like an e to the minus s sitting in front, which isn't really any easier to deal with. So Z transforms are definitely nice for dealing with discrete time systems. But let's play around with going the other direction a bit. What if we had something called the smiley transform? So what I'm going to do is imagine that I have a continuous transform. Let's create a new transform for continuous time signals, and maybe let me put a tilde on top to remind myself that this is not the standard Laplace transform. This is a new weird transform. How about let's take our continuous time function, but instead of multiplying it by e to the whatever, let's multiply it by smiley face to the minus t dt. So this is kind of like a Laplace transform in that we're dealing with continuous valued functions, but notationally we're trying to write something that's closer to what the Z transform looks like. So let's say you wanted to use the smiley transform and you wanted to figure out what the appropriate derivative property of this would be. Well, let's take the derivative of x of t and plug it into our smiley transform. Okay, so we need to do the integration by parts. Let's say this function here is our u, and then this derivative, the x and the dt, this is our dv. So v is going to be just xt, and then u, I need to remember how to take this derivative. So I need to be careful here because I'm taking a derivative with respect to t. This is not something like taking the derivative of t cubed where the t is what we're taking the power of. It's not something like that. So the way to handle this is to rewrite the smiley face as e to the log of our smiley face, just as a number, with the minus t out here like this. Okay, so let's see what happens when we take the derivative here. Well, that log smiley face is just a constant. It comes out in front by the chain rule. I need to make sure a minus sign goes along with that constant. Then I'm left with e to the minus log smiley face t, and I can just take that e to the log to rewrite this again as smiley face minus t. So if smiley face was e, log of e would be 1, and this would look like your regular derivative of an exponent. But I have this constant out in front because the base isn't actually e, it's something else. Using integration by parts, this expression is equal to uv minus the integral of v du. So substituting everything in here, I'll have the u, I'll just have smiley face for the u minus t. What about the v? That's going to be xt, evaluated at t going from 0 with that minus superscript to infinity minus integral of v, which here is this x of t, times the du. So I'll have minus with this log smiley face times the smiley face with the minus t. Oh, I need to remember to put the differential on here. So there's a dt. To match the way I've traditionally written this, let me write this as t equals infinity, although it's clear what I meant here. So, as usual, I'm going to assume that as t goes to infinity, this term is going to go to 0. It sort of had to for the Laplace transform to exist to begin with. And then when I plug in the t with the superscript minus for everything in here, this turns into a 1. And I'm just left with x evaluated at this lower limit here. The minus signs will cancel, which will give me a plus. I need to be very careful not to forget the minus sign in front of here that results from the fact that we're plugging in the lower limit. I can pull the logarithm here out in front, and then I have this integral xt with the smiley face to the minus t dt. And of course, this looks familiar. This is just that smiley transform. Let's remind ourselves what the smiley transform looked like. So, I can rewrite this as log smiley face times the smiley transform minus my initial condition. So our smiley transform looks a lot like this setup, except I would have log smiley here. And again, the way I'm writing it here, I'm assuming the initial condition is 0. And actually, I should really say the same thing for the Z transform version. In 2026, we didn't really deal with initial conditions in the same way. If you take ECE4070, they'll probably get into that. The most general form of the Z transform formula has a minus initial condition sort of thing in it. Let me put some parentheses around here to make the precedence clear. So you could use the smiley transform, but having to write log all the time when dealing with differential equations would get awfully annoying. And at some point you would say, hey, I'm writing log smiley face so much, why don't I do a change of variable? And then you would go through the same kind of reasoning we did in the previous lecture, except the other direction. People who are avid fans of various movies, books, television shows, games, have a term that they refer to as headcanon, which is a concept about something that happens in that fictional universe and why things happen that's not part of the official canon as stated by the creators of that particular art. It's something that the fan comes up with. My headcanon for Laplace transforms is that they might have started with something that looked like a smiley transform, realized that all of these logs were getting a bit crazy, and then did a change of variable to come up with that. There's actually a MIT professor who has a lecture about Laplace transforms and differential equations who goes through a kind of derivation along those lines by starting from the idea of solutions of differential equations via power series. So you can check that out if you're interested. So in the next lecture, what we're going to do is we're going to return to the question of how these transforms map back and forth. So this mapping from the S-plane to the Z-plane and from the Z-plane back to the S-plane, with the general caveat that you have to treat this logarithm a little carefully. That's something we're going to focus on in detail in the next lecture.